All right, I'm going to spend the next few minutes talking about taking what we have learned about equilibrium, chemical equilibrium, to the next level as it specifically applies to acids and bases. From the beginning, I want to remind you that we said an acid is anything that increases the hydronium in water, and a base is anything that increases the hydroxide in water. But these things naturally exist in water on their own. That's why we have to say increases rather than adds. Here's what it looks like. Every time two water molecules collide, there's at least a small chance that a hydronium ion or a hydrogen ion is transferred from one water molecule to the other. So these two water molecules collide, the hydrogen moves over and sticks to the other one. This leads to the natural formation of both hydronium and hydroxide in the water. Now here it says label the acid and base in the image above. This will be good practice. An acid is anything that is a proton donor. If this water molecule on the left is donating, then it is the acid. Obviously, the second water molecule is receiving that hydrogen, so it is acting as a base. Now, after the donation occurs, after this hydrogen transfer, they have another name, the remaining species. The analogy I like to use is if you're playing catch. You're hanging out in someone's backyard and you're throwing a ball back and forth. There is no thrower or catcher. You're both throwing and catching. So the one that throws the ball, as soon as they finish throwing the ball, they are now set up to catch the ball. You can think of this hydrogen as the ball that's being thrown, and it is landing in this spot. The thrower is the acid, the catcher is the base. But as soon as the ball is thrown, the thrower now has a hole, and the catcher now has the ball. This is important because after a species donates a proton, the result is called a conjugate base. So this hydroxide here used to be an acid, but after it donated the proton, it is now available to receive a proton, so we call it the conjugate base. Likewise, the base, after it accepts the proton, results in a conjugate acid. Ca. Once it has received an additional proton, it is far more likely to donate that proton in further reactions than it is to receive any more. So what initially counted as a base can now be called a conjugate acid because it may behave like an acid in further interactions. When hydronium and hydroxide collide, there's a chance that that hydrogen will return to the conjugate base. It will go back the other way. As a result, this autoionization of water is a reversible reaction. When H2O reacts with H2O, it could form hydroxide and hydronium. But when hydroxide and hydronium interact with one another, they could form two water molecules. So as we look at this, if water contains both hydronium, which is our acid, that's not the word acid, which is our acid molecule, and hydroxide, which is our base molecule, is water an acid or a base? Before I said it can act like both, but in reality, pure water is actually neither. Because why? If acids and bases neutralize one another, then water is neither because it contains equal amounts of both hydronium and hydroxide. Every reaction in the autoionization of water produces exactly one hydronium and exactly one hydroxide. Those hydronium and hydroxide particles cancel each other out, meaning that water will not behave as an acid or a base because it is neutral. It's canceled itself out. So how do we use this information to describe acids and bases? At equilibrium, we can measure the exact amount of hydronium and hydroxide that are formed in water. It's basically a equilibrium reaction. So if this is my H2O and this is, let's say, hydronium, then if I start with pure 100% H2O, you'll see an equilibrium reaction that looks very similar to what we saw with our soda. Now, the H2O is favored, which means you're going to have a ton more water than hydronium that forms, but in this case, the amount of hydronium that forms is exactly 1.0 times 10 to the negative 7 moles per liter. It's not very much. How much hydroxide is formed? Well, if one hydronium and one hydroxide are always formed at the same time, that means we are seeing 1.0 times 10 to the negative 7 moles per liter of hydroxide at exactly the same time. Now, if you're wondering why I have hydronium and hydroxide in brackets, that is a shorthand that simply means concentration. So the way acids and bases work is while water naturally has some hydronium and some hydroxide, if an acid is something that works to increase hydronium in water, then when I increase this hydronium so that there is more hydronium than hydroxide, we have something that is acidic. If I add the same amounts of hydronium and hydroxide, we have something that is neutral. And if instead I add a base that works to increase hydroxide in water, then more hydroxide means I have something that is alkaline. Let's practice this idea. If the concentration of hydronium in a solution is 3.3 times 10 to the negative 14 molar, and the concentration of hydroxide is 3.0 times 10 to the negative 1 molar, is the solution acidic, basic, or neutral? So basically, we're just trying to say my concentration of H3O plus equals 3.3 times 10 to the negative 14, and my concentration of OH minus is 3.0 times 10 to the negative 1 molar, and we're just asking which one has a bigger number. Now, you might be tempted, I wrote negative 4, that was supposed to be negative 14. You might be tempted to say, oh, 3.3 is bigger than 3.0, so obviously there's more hydronium. But scientific notation comes into play. Remember, times 10 to the negative 14 means I have a whole bunch of zeros before I get to that 3.3. And times 10 to the negative 1 means I have to move the decimal place just once. So in this case, the hydroxide is much, much larger. And that's kind of a pain to have to imagine and think about all those moving decimal places. And so this is where the idea of pH has come from. No one likes dealing with exponents, so we use the pH scale instead. You start with concentration. In this case, the concentration of our hydronium was 3.3 times 10 to the negative 14 molar. And we don't like exponents. We think exponents are gross. So we randomly decided, what if I just take the logarithm of this? There's genuinely no purpose, no point in taking the logarithm other than to make this number not have an exponent. So regular logarithm of 3.3 times 10 to the negative 14. When you put that into your calculator, it roughly spits out the number negative 13. Oh, but negative numbers, I don't want to have to think about that. So we decided, let's just randomly multiply it by negative 1. Negative 13 times negative 1 equals, I didn't need the x there, equals positive 13. This is called the pH. pH is not a direct measure of anything. pH is an alteration of the literal concentration of hydronium. We just do some magic to that concentration number to make it easier to work with. So the pH of the final product was 13. Here is the calculation that we just did. If I know the concentration of hydronium, then I need to take the logarithm and then multiply it by negative 1 in order to figure out the final pH. Now, pOH is very, very similar. Instead of measuring the concentration of hydronium, it's measuring the concentration of hydroxide. So the pOH is where I take the negative log of the concentration of hydroxide. We could have just taken this number up here and plugged that into our logarithm to get what's called pOH. Now, because water always has 1 times 10 to the negative 7 of both hydronium and hydroxide in total, then when you add pH and pOH together from the same substance, they should always equal 14. Now, these other two equations are how I take my pH and work backwards to find the concentration. If I know that the pH is 13, for instance, and I want to know what the concentration is, I would just say concentration of hydronium equals 10 raised to the power of negative 13. If my pH is 13, then I take 10 to the power of negative 13, and that will give me my original concentration back. So let's use this real quick to calculate the pH of pure water. If in pure water I know that the concentration of hydronium is 1.0 times 10 to the negative 7 molar, then what I need to do to find the pH of water is take the negative log of 1.0 times 10 to the negative 7. If I grab my computer calculator and work this out, it would be, I do 1 times 10 raised to the, where's my negative button? Negative 7. Gives me that tiny number. And then I take a logarithm of it, and then I multiply it by negative 1 to get my final pH. The pH of water, based on this concentration, is exactly 7.0. If I want to know the pOH of my water, let's do that over here. pOH equals the negative log of the concentration of OH minus. So if my concentration of OH minus is 1.0 times 10 to the negative 7 molar, you can see my math is going to look exactly the same. Negative log 1.0 times 10 to the negative 7 molar. And so as a result, my pOH is also going to be 7.0. If I take pH plus pOH, it should always equal 14, and in this case, it does. So what I want you to do for the rest of your homework is see if you can take these equations and solve these 5 math problems. We're going to see if we can find the pH of the 5 problems here. If you have questions, please send me messages. Hopefully, this isn't too slow. Thanks. Bye.